Good morning all. Today we are going to see about the asymptotic notations in design and analysis of algorithm. We are having three kinds of asymptotic notation: big O, big theta, big omega. These are the three type of notations, and we'll be having also small o, small theta and small omega. But rather most probably we will be using the big O, big omega and big theta notations. Big O notations asymptotic is always less than the function of n, which is less than or equal to the given n number of value. Same as is theta of n in asymptotic notation, which is equals the function of n and the g of n, that is given number of n. And in omega notation in asymptotic, it is greater than f1, that is function of n, which is greater than or equal to the g of n, that is the constant value. Let's see the definition. First we'll go for big O. Here the f of n, which is equal to big O of g of n, there exists the positive constant c and n naught, such that we'll be having 0 which is less than or equal to f of n, which is less than or equal to c g of n for all n which is greater than or equal to n naught. So for example, if we go for f of n which is equal to big O of n square, then it calculates the n number of times the process has been calculated, that is n square of time how the number of process has been calculated. So that has to be monitored over here. So we'll choose some constant c and also the value of n naught. So for every value n larger, will be having f of n which is less than or equal to the constant value of n square. So these are the more process, that's why it is greater than or equal to c of n we are going to see. So this is the overall visualization of big O of g of n. Here we'll be having the n naught, that is the constant value, all, and c also will be having a constant value c g of n. So always the f of n which is all greater than or equal to g of n. So f of n which is greater than or equal to g of n, which implies the big O of n. Next we will go for big omega notation. So omega here where we always say as the lower bound part. So lower bound in the sense f of n which is always equals to omega of g of n. There exists the positive constant c and n naught, such that 0 which is less than or equal to f of n, which is greater than or equal to c g of n for all n greater than or equal to n naught. So always n square which is equal to omega of n. So always it is equals. So if, say for example, take as phi of n which is down towards here and f of n is up towards there. Then takes for theta. Theta is always, it's not a tight upper bound. In other words, it's called as n which is equal to big O of n square. That is big O. The theta provides the tight bound. It's always the tight bound. So f of n which always equals to theta of g of n. Let's see here. We'll be having f of n and we'll be having two constant value, that is c1 of g of n and c2 of g of n. It implies between the c1 and c2, so that it always called as it equals with the g of n. F of n is always equals with the g of n. Let's see the all kind of the notations over here, that is big O, small o, big theta, small theta, big omega and small omega. So if you take it as the big O notation, it's always higher, same as it is the small o2, and omega, big omega also, it is lower than the function, same as it is small omega. And if take for theta, it always implies equal to f of n. So this is the overall graph of the visualization of the asymptotic notations. So n naught is the constant value which is replied over here. So these are the process. Simply we'll take an analogy with the algorithmic operator. F of n which is equal to big O of g of n, it implies a which is less than or equal to b. F of n which is equal to omega of g of n, which implies a which is greater than or equal to b. And finally f of n which is equal to theta of g of n, which implies A which is equal to B. So this is the final analogy how we compare with the mathematical analysis. Thank you.